Hello everybody. In the next videos we will talk about the multivariate Gaussian. I assume everybody is familiar with the univariate Gaussian. Its density has the well-known bell-shaped function graph that I quickly sketch here. So assume that this is the mean value 0. Then we have something like that. Okay. So the more general form of the Gaussian, the multivariate Gaussian, is depicted here. And we see that this is the way you would write the Gaussian for an arbitrary number of dimensions. What we want to do in this deck of slides is to find out some of the many useful properties of this density. A quick word about notation. We often use this expression here to denote the density, but we also write something like this to denote the distribution, which means that this is a random variable x from a Gaussian with these two parameters. Okay, so the distribution has these two parameters, mu, a vector, and sigma, a matrix. And furthermore, we assume that sigma is symmetric and positive definite. So if you're not totally sure what positive definite is, please look it up. So the most two important basic facts about the Gaussian are shown here. The mean of a random variable distributed according to such a Gaussian is the mu vector, and the covariance matrix is sigma. Sometimes the covariance matrix is a little bit difficult to understand, at least at the beginning, so try to think of this question here. What are the diagonal elements of sigma? And furthermore, as a sort of a training exercise, you should be able to show that the expectation is linear. So this is of course a general property, and you should be able to prove this identity. Okay, so I said that we want to understand properties of the Gaussian distribution. The first property that we will look at is what's the geometric shape of this density, right? So if you want to draw it in 2D, how would we draw it? And you probably have seen this. The bivariate Gaussian is often drawn as an ellipse, and we want to find out with math why this is the case. And in order to see why this is correct, we need to do a little bit of linear algebra. Okay, so first we do an eigen decomposition of the covariance matrix, and because it's real and symmetric, you can write it like that, where U is an orthonormal matrix and delta is a diagonal matrix of eigenvalues. So delta looks like that. There's only entries on the diagonal and everything else is 0. And remember, we said it's positive definite, which also means that all the diagonal elements are larger than 0 actually. And here, from the orthonormal property of U, we also know, by the way, that the inverse of U transposed, also that the inverse of transpose is U. Okay? So, armed with these facts, we can write the inverse of the covariance matrix can also be decomposed by utilizing what we have already written. And so this is a very interesting property, interesting equality, and try to make sure that you understand how to get from here to here, because knowing how to do this will be pretty helpful for later algorithms in our course. Okay, and remember, we assumed full rank, which means there's no problem of dividing through an eigenvalue, because all these eigenvalues were assumed to be larger than 0. Okay. So the interesting part of the density is this expression, because this expression encompasses x, right? The free variable x here, and we want to reshape this expression in such a way that it turns out that yes, this can be drawn, the function graph of this expression can be drawn like an ellipse. So we take this expression, we plug in our decomposition for the inverse covariance matrix, then we do a little bit of shuffling. In this case, we put the sum in front of the whole expression and we shuffle some terms around so that we get to this scalar product, right? Remember, scalar product means the result is a number, a real number, and we denote this real number by yi, and also see that this expression here is the same expression, only swapped, but a real number is also the result of this, and of course this is also yi. And therefore, we can write this complicated looking quadric as this rather innocently looking sum of squares divided by positive numbers. So how does this connect to an ellipse? Well, an ellipse in 2D is represented by this formula. So x and y being the two coordinate axes, and we often fix the radius to be 1. And now you see for d equals 2, we have exactly this. Okay, so we have a formula that represents an ellipse. Right? Remember, lambda 1 and lambda 2 are also positive. So we have the same functional form that we have here, we find here. And that's actually the proof why a Gaussian density is represented, geometrically at least, by an ellipsoid. So let's look at a couple of examples. Okay, so what we quickly want to find out is what are the corresponding covariance matrices in these three cases. So this is a standard circle. So the covariance matrix actually looks like this in 2D. So there's only diagonal entries and both entries are the same. This one, it's an ellipse, but still axis aligned. Okay, so something like that. And we know that lambda 1 is larger than lambda 2. And here we have an arbitrary positive definite covariance matrix, and let's say so diagonals are like that. And here, because it's symmetric, of course, same to anti-diagonal entries. And a good exercise for you probably would be to take an arbitrary positive definite matrix 2 by 2 and try to find the main two axes of the underlying ellipse and try to also draw these isolines here. Okay, so this is the first property of the Gaussian. Next one is also a very important characteristic of this distribution. In a very abstract form, it means that Gaussian is closed under linear transformation. What does that mean? So assume we have a random variable x and it's distributed according to a Gaussian with mean value mu and covariance matrix sigma, then a new random variable y, which is a linear transformation of x. So linear transformation means matrix A times this x. This new random variable y is a Gaussian. B, it has this mean, and C, it has this covariance matrix. You can prove B, this, and C on your own by simply looking at the definitions of expectation and covariance. And you probably should do this as an exercise. However, proving that Y is itself actually a Gaussian is a little bit more involved, and we are not looking into it. But it's pretty important that you remember this fact, and these two things you usually can derive on your own, actually. Okay, later on we will see that this property is constantly used in several algorithms. Okay, so now we want to do some learning. Remember, what was learning actually? So learning with the coin, for example, meant we had a couple of observations, and then given these observations, we wanted to deduce the underlying parameter. We wanted to do some inference. So with the Gaussian, we have these two parameters, the mean and the covariance matrix. So let's try to deduce these parameters from observations. Okay, so we assume we have n observations xi. These xi's are random samples from this density we are looking at. And now we want to find out what's the best parameter mu for these set of observations. Okay, so of course we do maximum likelihood estimation, write down the likelihood, and the likelihood is this expression here, and remember again, what is the underlying assumption here? Well, we assume all these xi's are independently and identically distributed. So we can write this product, and the product is not nice to us, so we write the log in front of it, and in this case even the log is not completely nice to us, so we write the negative log in front of this to kick away some annoying negative signs actually. So if you do minus log of this expression, you would get this larger terms here, and this is the function, the maximum likelihood function that we are working with. And what does that mean? Again, it means we're looking at the first derivative of this function with respect to the mean mu and try to find the best mu for this expression. So let's do this, and in order to be able to do this, let's rewrite this expression here into smaller pieces. So we do this, a little bit of multiplications, and we get these smaller chunks that are easier to handle. And for example, you see there's no dependency on mu here, so when looking at the first derivative, this is definitely something that will get lost. So for first derivatives with respect to vectors and later on matrices, it's pretty helpful to have a set of identities. In particular, in our case, as it turns out, this identity here and this identity here is extremely helpful. And if you are interested in finding more of these identities, go to Google and search for the matrix cookbook. Okay, so given these two identities here, we apply this to our log likelihood, we compute the first derivative, and out we get this here. Okay, so this is the first derivative of the negative log likelihood with respect to the mean value. And of course, the goal is to find the mu such that this is equal to 0, so 0 vector. Okay, so doing this, doing a little bit of algebra, we find out the maximum likelihood estimate for the mean mu is actually the empirical mean. And of course, this is something you probably know, but now we've shown this in a mathematically rigorous way. And let's continue immediately to do the same thing for the covariance matrix. So we want to do a maximum likelihood estimation of sigma. In order to be able to do this, it turns out that we need another linear algebra operator, the trace operator. So the trace of a matrix, of a quadratic matrix actually, A, is simply the sum of the diagonal elements. And it has this nice cyclic property. So trace of ABC is trace of BCA is trace of CAB. And so why is it called cyclic? Please have a look at it in a very detailed way. We see that we cycle, we are allowed to cycle matrices, and supposedly the result stays the same. That's a nice exercise for you actually to show that this is correct. These three expressions are actually equal. So where do we apply this? So the trace of a real number is of course the real number. So this is a real number, then I'm allowed to write trace in front of this, and now I can do a cyclic property shift, cyclic shift here, and suddenly the real number became the trace of a complicated looking matrix. So this seems not very intuitive at first, but as we will see, that's a very nice trick to have in the backhand. So we apply this specifically to our quadratic expression here and simply cyclically shift terms. And we need another ingredient for our maximum likelihood estimation of the covariance matrix. In particular, what we need is that we can write the determinant of a matrix as the inverse of the inverse determinant. Okay, so putting everything together, let's write down the negative log likelihood again, in this case with respect to the inverse covariance matrix. So only terms with the inverse covariance matrix are interesting, so this term and of course this term here. And now we need to look at the first derivative, and again we need a couple of identities from the matrix cookbook. Specifically we need this identity and this identity, and here you see that's the reason why we introduced the trace operator, because in the matrix cookbook there is a very helpful identity that allows us to compute a first derivative with respect to a matrix. Okay, so that's done here now. The first derivative of the negative log likelihood with respect to the inverse covariance matrix is this expression here, and the goal is of course to be equal to 0. So this is a matrix now, a matrix full of zeros. And if we do some algebra here, we find out that the maximum likelihood estimate of the covariance matrix is actually the empirical covariance matrix. And again, this is something that you probably know from somewhere, but now we've shown why this is mathematically correct. And of course, the inductive hypothesis here was that we are doing a maximum likelihood estimation. So this ends this video, and in the next video we will continue to look at some more properties of the multivariate Gaussian.